Adiponectin, a hormone secreted almost exclusively by adipocytes, stands out as one of the most powerful links between adipose tissue and systemic longevity. Its unique ability to enhance insulin sensitivity, dampen chronic inflammation, and promote cellular resilience positions it as a molecular bridge between metabolic health and aging. Contrary to the historical narrative that fat merely shortens lifespan, the adiponectin story reveals that fat, when functioning optimally, actually secretes molecules that extend it. This hormone exemplifies the notion that healthy fat is not just benign, it is actively protective. Animal studies offer some of the most compelling evidence for adiponectin's role in lifespan regulation. Mice deficient in adiponectin show premature aging phenotypes, accelerated insulin resistance, increased systemic inflammation, and a significantly shortened lifespan compared to wild-type controls. Their tissues exhibit greater oxidative stress, poor mitochondrial function, and earlier onset of metabolic dysfunction. In contrast, transgenic mice engineered to express higher levels of adiponectin live markedly longer. They are protected from age-related insulin resistance, hepatic steatosis, and atherosclerosis. Their organs, particularly liver, muscle, and heart, show reduced inflammatory signaling and preserved mitochondrial health deep into old age. One reason adiponectin is so uniquely protective is its dual role in both metabolism and inflammation. It enhances the action of insulin in skeletal muscle and liver by promoting YMPK activation, a critical cellular energy sensor. YMPK, in turn, stimulates fatty acid oxidation, improves glucose uptake, and suppresses inflammatory signaling pathways such as NF-B. In doing so, adiponectin helps cells maintain energy balance without resorting to stress responses that promote cellular aging. Its anti-inflammatory properties are equally powerful. Adiponectin inhibits macrophage infiltration into tissues and shifts immune cells away from the pro-inflammatory M1 phenotype toward the anti-inflammatory M2 state. This is crucial as chronic low-grade inflammation, or inflammaging, is a known accelerator of biological aging. In humans, observational data strongly support these findings. Higher adiponectin levels consistently correlate with better insulin sensitivity, lower visceral fat, and reduced cardiovascular risk. Centenarians and healthy elderly populations often display elevated adiponectin levels compared to age-matched peers with chronic disease. Importantly, these higher levels are not merely a passive marker of good health, they appear to be contributory to it. Longitudinal studies suggest that individuals with higher baseline adiponectin are less likely to develop type 2 diabetes, hypertension, or metabolic syndrome over time. Adiponectin also plays a role in tissue regeneration and vascular health. It stimulates the proliferation and migration of endothelial cells, enhancing angiogenesis and tissue perfusion. This may explain, in part, its protective effects in the heart and brain, where vascular decline is a key contributor to age-related disease. Moreover, adiponectin can modulate autophagy, a cellular recycling process essential for removing damaged proteins and organelles. By promoting autophagy, especially under nutrient stress conditions, adiponectin helps cells maintain proteostasis and mitochondrial integrity, two central pillars of cellular longevity. There is also emerging evidence that adiponectin crosses into the central nervous system, influencing brain metabolism and neuroinflammation. In animal models, it has been shown to protect neurons from oxidative damage, reduce amyloid plaque deposition, and support synaptic plasticity. These neuroprotective effects suggest that adiponectin may have broader roles beyond peripheral metabolism, potentially extending to cognitive longevity and resilience against neurodegenerative diseases. A paradox sometimes emerges in clinical studies where extremely high adiponectin levels are found in late-stage chronic illness, such as advanced heart failure or chronic kidney disease. However, these instances are generally understood to reflect a compensatory response, an attempt by the body to counteract rising inflammation and metabolic decline, rather than evidence of adiponectin toxicity. In fact, the early and sustained presence of moderate to high adiponectin levels remains a consistent predictor of better outcomes in otherwise healthy individuals. What all this highlights is that adiponectin is not just a hormone of short-term metabolic regulation. It is a systemic protector whose presence tracks closely with functional capacity, disease resistance, and lifespan itself. And its origin in fat cells further reinforces the argument that adipose tissue, when healthy, is not a biological liability, but a longevity organ in its own right. Thus, efforts to support or enhance adiponectin secretion through lifestyle, pharmacological, or even nutritional means are fundamentally efforts to extend health span. Caloric moderation, regular physical activity, and certain polyphenol, like resveratrol or curcumin, are known to increase adiponectin levels. So do omega-3 fatty acids and thiazolidinediones, TZDs, though the latter come with other trade-offs. The future may lie in strategies that specifically upregulate adiponectin or mimic its actions without the risks associated with broader metabolic modulators. In the end, adiponectin encapsulates a larger truth. Fat is not merely a caloric surplus or storage depot. It is an active participant in the orchestration of aging and survival. And through molecules like adiponectin, adipose tissue reveals its unexpected and vital role in the maintenance of health, resilience, and life itself.